Welcome to this course on deep learning in health, one of the first of its kind. Deep learning offers some of the most spectacular new advances in medicine and health, delivering stunning levels of expertise to healthcare providers and democratizing medicine with the ability to help those from the most disadvantaged in sub-Saharan Africa to Appalachia, as well as bringing elite medical center experience to smaller cities and rural areas in the United States. For instance, if you're having a CT scan taken in a small rural hospital emergency department, as I did recently, and this is in the middle of the night, you could have a deep learning system read your scan with an expertise as good as the very best radiologist in the world, nearly instantly, perhaps saving your life. If you love new applications, computer programs, or apps on your smartphone, you're going to fall in love with deep learning. The applications are fabulous and now easier than ever to access and apply, whether you're a healthcare professional or one of the great administrators that make American healthcare the very best in the world. So, the power is at your fingertips, and it's phenomenal, performing in minutes what used to take the world's largest supercomputer days to years before the advent of deep learning. If you're looking for a career change, there's no better place to look than artificial intelligence, where the talent market is described as white hot. Gartner reports that business value created by AI will reach $3.9 trillion in 2022. In healthcare, leaders are looking every day for AI professionals to add to their teams. How well can you do? The average for high-paying AI jobs in 2019 was $142,858. That's the average salary for machine learning engineers, the subject of our last course. Deep learning engineers rank second on Indeed's list of the top roles in job listings seeking AI or machine learning skills. The highest demand is for computer vision jobs like autonomous driving, advanced robotics, and facial recognition systems. Have a look at Indeed.com for jobs near you to get a sense of your local job market. I'm a huge believer in domain expertise. As an example, a great friend of mine is psychiatrist-in-chief at one of America's leading hospitals. His papers have been quoted over 80,000 times in the literature, and he has authored or co-authored over 800 scientific articles. He clearly has a domain-level command of the breadth and depth of depression worldwide. This level of domain expertise helps enormously in the design of an artificial neural network and the quality of the research and data you feed into the ANN, which is, of course, short for artificial neural network. There is a word for healthcare providers who also know deep learning. They are called bilingual, and that is the greatest value in all of artificial intelligence. Having a domain expertise, such as cardiology, or the management of a large medical center, and a solid grounding in deep learning. This course allows you to understand all the fundamental high-level concepts of deep learning and also some granular level knowledge so that you as a healthcare professional or administrator can help data scientists design the best deep learning systems. You need not have much detailed knowledge because you're probably not going to be constructing these neural networks from scratch, but you want to be able to add your expertise, which vastly improves the system. That's why it's so critically important for doctors, nurses, nurse practitioners, physician's assistants, healthcare administrators, and others to understand neural networks as the amount of medical data mushrooms. Medicine has become the most data-intensive of all subjects. Compare, for example, genomics with all the data contained within the human genome. The human genome is capable of storing 215 million gigabytes. Each cell has 360,000 messenger molecules called mRNA. If DNA were used as a memory storage system, then all the world's data could fit in a single room, since it's ultra compact and could last hundreds, if not thousands of years, as we have seen with recent archaeological digs which have recovered a DNA from thousands of years ago. Unfortunately, the cost of encoding is so great that we're not going to have genomic hard drives anytime soon. Medical data is rapidly expanding and is expected to surpass social media, YouTube, and perhaps all other fields. Businesses can generate a large volume of data, yet it is the tremendous complexity, diversity of medical data that makes it so incredibly challenging. However, the rewards are astounding when you look at the ability to develop new drugs and treatments, vastly enhance the accuracy of diagnostics, and offer incredibly precise personal medicine. And as we know, personal medicine is where all of medicine is going to give you the best possible result. The volume and complexity of these data present new opportunities, but also pose new and enormous challenges. Automated algorithms can pull out important patterns leading to actionable knowledge, such as alerting doctors to an impending cardiac arrest in an ICU patient so that they can rescue that patient before they have a cardiac arrest. Neural networks require large training sets to attain high accuracy and usefulness. As a general rule, you may want to use machine learning for small training data sets and artificial neural networks for enormous data sets. One reason that deep learning is so popular in medicine is that medicine has the largest big data sets of all. And by the way, we're going to explain these terms, deep learning, machine learning, artificial neural networks in just a minute. So first, let's look at a key problem that deep learning can solve. So here's the problem. As many as 20% of lung and breast cancers go completely undetected. A company called Linnet has combined deep learning and 3D visualization to detect these cancers. Their technology increases the chance of detecting them by as much as 86%. They do this by going well beyond what's done now with the usual family history and diving into genomics. Let's have a look. Breast cancer identification. Breast cancers have at least 50 important genetic markers which are used for therapeutics and diagnostics. And these, of course, allow researchers and physicians to divide them into 4 specific subtypes of breast cancer. However, even within these subtypes, there is tremendous variation. Now, new approaches pull together this molecular level data with mammograms and other imaging techniques and with the electronic health record, which of course is so hard to read because the data is so poorly put together. This wasn't practical or even possible before the advent of deep learning, and certainly not as a scalable system to offer as a potential clinical service. You'll find that deep learning picks right up from where we left off with the machine learning course. You can use deep learning for simple binary, and that's either or, yes or no, cancer, no cancer, or classification problems, and can use the same Python libraries to examine and visualize your data, such as MATLAB, Matplotlib, and Seaborn. We saw that one coded example of heart disease we did had a poor outcome in our molar learning course, just 64% accuracy. The artificial neural network, which we'll look at shortly, is likely to improve on machine learning. Also, the ANN loves tons of data, and the more data it has, the better it does. Like machine learning, in deep learning, the computer does the programming in the sense that it creates the algorithm. To be clear, an algorithm is a mathematical formula that nearly perfectly describes the data and which the computer figures out for you after it is trained on the data that you have fed it. The artificial neural network really excels at nonlinear data. That is, we all know that a perfect straight line works incredibly well in linear regression, allowing you to perfectly pick points off of it. But if the data set describes a triangle or a circle or a crescent, it's totally stuck. And this is where deep learning shines and where a linear regression model will utterly fail. Non-linear data. So let's take an example. And this is in a wonderful program called TensorFlow Playground. Look at this very cool animation, taking data that the computer initially thinks is linear. You see that straight line in the background there? Now, look at what the artificial neural network does after the data has been run a couple of hundred times. It's a real shape. It's a triangle. The computer, like in machine learning, is also excellent at what we term feature selection. That is, if you're at risk for heart disease, what are the most important risks? Not in general, not in a big study like the Framingham study, but for you. Blood pressure, cholesterol level, age, and sex would emerge at the top. However, if you have a health survey with hundreds of features, such as new genomic data or metabolomics, which you looked at in the motor learning or machine learning course, what would you know to be the most important? You wouldn't. The A&M will tell you which is the one that you experience as the greatest risk. And you'll have that tremendous aha moment saying, gee, I never would have guessed it. And that's the wonderful thing about neural networks and artificial intelligence is presenting answers you just never would have thought of. ANNs, or artificial neural networks, can solve simple problems like a linear regression, which allow or only require a very shallow network. You find that you use both machine learning and deep learning techniques together to solve problems and achieve the very highest accuracy. However, with huge data sets and vastly improved computing power, artificial neural networks will outperform machine learning. Just to be clear, deep learning refers to the layers between the input values and the output layers. If you have roughly 2 or more internal layers, then you have deep learning. Adding these layers often adds precision and increased accuracy. These deep layers are where much of the magic in deep learning is. Let's have a look at a TensorFlow model. First, increasing the number of neurons within a deep layer, and then increasing the total number of deep layers. You can see this easily in the tremendous number of new connections and tremendous flow of data here. You can see the stunning improvement too in performance. Big picture. You probably remember from statistics in algebra the formula of y equals x, or whatever it happens to be. But you have those two variables. For instance, a simple linear regression will be y equals a plus bx. Well, those x's are the input values like blood pressure, weight, sex, cholesterol for heart disease prediction. The y is the predicted value which would follow on the right side that you'll see here of the neural network. In the examples we'll go over, this could be predicting whether or not a patient has heart disease in the first place or what class of disease they have in the second. In between the input and output layers, you can see the deep layers. The artificial neural network is solving for the constants so that you can create a formula or algorithm which describes your data set. In the example above, the A and B basically are the constants that the formula comes up with, so it will work. You'll notice one feature in this course, and that is repetition. Since so much of this is so new and it's so easy to miss a point, I repeat key pieces in different ways to be sure it's absolutely crystal clear. I know, in having taken many courses online myself, that I was hugely frustrated getting stuck because I didn't understand or couldn't hear a single simple command. It was that much that I had to abandon the course, or at least write the instructor and beg for some help. So apologies up front, but this repetition really will be helpful in terms of making this clear. In the end, that's all we want. We want you to walk away with a very clear understanding of what deep learning is. Okay, we mentioned it a number of times, but now let's look at the artificial neural network. Since 1943, scientists looked for a way to replicate how the human brain is constructed to create an artificial neural network which could process data like the human brain. This is a hugely ambitious project. It was a brilliant concept at the time, but decades before the computing power was available to make neural networks possible. Even with vastly improved computing power today, the task still remains Herculean to approximate even the tiniest capacity of the human brain. Now here's why. Let's look at the human brain in great depth. It has 86 billion neurons. Each of these neurons then connects to 10,000 other neurons for a total of 1,000 trillion connections. Almost unimaginable, and certainly unimaginable to most data learning experts. The human brain's memory capacity may be as much as 1,000 terabytes, which is compared to the Library of Congress, which is just 10 terabytes. It's the connection between these neurons that makes the brain as great as it is and so facile in solving so many problems. So, how does the artificial neural network differ? Let's take a look. First, the artificial neural network has nowhere near as many connections as the human brain. Second, it doesn't have the incredibly subtle power of the brain to turn each individual neuron on or off in incredibly subtle amplitudes. And then the artificial neural networks receives inputs as numerical values. The artificial neuron triggers only when it reaches a certain threshold, which, if you take a look at it, is far less subtle and complex than the human neuron, each one of which can fire at different thresholds. And third, even the most complex artificial neural network has far, far fewer input nodes. I looked at a phenomenally complex astronomical model. Love astronomy, and of course, I was looking at all these galaxies and nebulae. Now, they had 8,000 input nodes, which is almost infinitesimally small compared to what you're going to find in the human brain. So, no need to worry about your day job yet. And of course, thankfully for science fiction buffs, the artificial neural network doesn't actually think. So, first, let's look at all the pieces of the artificial neural network and look at their importance. Although the term artificial intelligence is thrown around quite a bit, these really are not yet thinking machines. Many of them have incredibly deep but narrow applications, like reading an X-ray or finding your way home with a GPS. Now, they can perform these tasks far faster than we can, but they're just tiny individual tasks. So for instance, your GPS or your smartphone may be able to figure 2 or 3 or 4 different routes home, given traffic and different conditions and kinds of roads and whatnot. And they're very, very good at that. But that's where it ends. It's just that deep application. So in machine learning too, look at how fast programs can find the quickest route to your destination, taking into account, again, the traffic in less than a second. If you and I were to sit down and do this and look at the maps and traffic conditions, it could take us 20 minutes. The great accuracy and flexibility of the artificial neural network has made tremendous gains over the very best machine learning algorithms, as we looked at in our last class. The algorithms created by deep learning systems produce higher accuracy and phenomenal speeds over best-in-class methods that computer scientists took years to design, rather than the few seconds or minutes that an A&M will take. In fact, you can design an artificial neural network all by yourself in a matter of minutes. You'll find these much more exciting than machine learning, far simpler to execute, and, as you take a look at it, with little of the drudgery. Pure excitement. Get ready to get excited. Let's go under the hood and look at all of the pieces of the artificial neural network. Why? First, appreciating how brilliant the underlying thesis is. But second, it's because these are the actual components you will be adjusting to build, train, and tune your own artificial neural networks models. So it makes so much more sense and is so much more satisfying to understand what you're building and tuning as you input data and fine-tune your model. Like understanding the accelerator, brake, steering wheel, speed control, and navigation system in your auto makes you a better driver. This will make you a much better deep learning specialist. In the second part of this introduction, we will look at the actual inputs into the code that create artificial neural network models and run them. Knowing the pieces of the ANN well will make this code incredibly clear and easy to use. That's the heart of this course, making the concepts crystal clear, then diving into the mechanics of setting them up. The neuron. The heart of a deep learning model is an artificial neuron. This connects to other neurons like the human brain does. While the artificial neuron is not exactly as complex as a real neuron, it does have the ability to do calculations and to transform its input before passing it on to the next neuron. So let's take a deeper look. The circle represents an artificial neuron. This receives inputs from a variety of other neurons as numbers, which are modified by a weight and a bias before they reach the neuron. We're going to explain that in a minute. Each individual input number is weighted based on its importance. So if its weight is, say, 0.8, then the neuron would be, in judging, say, high blood pressure, pass 80% of the value on. Pretty important. But if you had something like just a 0.3 or 30% for a resting heart rate, it would be of much less value. So that's weighting these. All the inputs to a single neuron are multiplied by their weights individually and then summed up and fed into the next neuron in the network. We'll cover weights shortly in great depth. However, the neuron gets to decide how or if it will pass this sum to the next neuron. The neuron does this with the help of an activation function. That is, the neuron only activates and passes on the sum if the activation function hits a predetermined limit or pass on a predetermined value based on this activation function. Very important part of the ANN. We'll look in greater depth at these activation functions, of which there are several important ones. The neuron sums up inputs and then calculates which values to pass on to the next neurons. Real neurons also send an electrical impulse, but are triggered by the very subtle release of neurotransmitters, so that signaling is far more precise and subtle and differs tremendously from one neuron to the next. So, hearing this for the first time, as I did, may seem incredibly complex. So let's break this down into smaller, digestible pieces for you to understand completely. As a unique feature, we will examine each of these parts and then see how they are connected to the actual computer code in an artificial neural network later in this course. So just before we do, let's take a preview of heart disease, because we're actually going to code this example later in the course. This famous case from the Cleveland Clinic seeks to answer a very simple question. Does this patient have heart disease or not? Now, I visited the Cleveland Clinic for many years. Their CEO for decades was Toby Cosgrove, a great pioneer in medicine who brought the clinic to its #1 ranking in heart disease. I've said in many cases over the years, always with a successful outcome. So now let's look at this data. You know, from very basic statistics, you might plot a straight line between blood pressure and risk of heart disease. But what happens when you have 13 different factors of vastly different dimensions? Say cholesterol to subjective pain during exercise or the result of a particular test. There's no straight line for that, and so the need for a much better method, which of course is deep learning. Since you may find the descriptions of neurons pretty abstract, let's try to make it all more concrete, taking a very simple model of an artificial neural network. We'll see them again, but here are the inputs from the Cleveland Clinic database. As a center of excellence in heart disease, the Cleveland Clinic has gone way beyond the basics to diagnose heart disease. So here are the basics. We're going to look at these in the database, and keep in mind, this is exactly what you look at if you were looking at an Excel spreadsheet. These would be all the columns across the top, beginning with age, sex, severity of chest pain, resting blood pressure, cholesterol, fasting blood sugar. But then the testing gets far more sophisticated. Old peak, that is, how much of a part of the EKG is depressed by exercise, is an indication of insufficient blood flow. It's actually called an ST segment. CA, this is the gold standard, catheterization, where a thin catheter is placed into the heart's blood vessels and the degree of narrowing is precisely measured. I've done this, I actually had this done this last year. It's just fascinating to watch your own heart beating as doctors thread a catheter in. Doctors thought in my own heart they saw a blockage, but an even more sophisticated test showed excellent blood flow through the suspected area. Phew! As you can imagine, with this diversity of data, doctors would be stumped in their search for a way to pull it all together, hence the artificial neural network. Let's preview how this would work. On the left side of the artificial neural network, you can see neurons, those circles. These are used to input the 13 kinds of data in the Cleveland Clinic data set. So let's match it up. Here are the inputs from a CSV file, it's very similar to an Excel spreadsheet, as they match up with the neurons. The magic, as you learn, is in these middle layers in this sandwich of neurons. You can see that every input neuron has a line connecting it to every one of the neurons in the next layer. At the right side is the output, with just one neuron as output. Why? Well, that's because the output is yes or no. We call that binary. Two choices. Again, yes or no, heart disease, no heart disease. Now let's focus on the second layer after the input. You see inputs from every one of the 13 items in the database. But what's more important, blood pressure or chest pain? The most important single concept in deep learning is understanding that these receive a weight. So I'll use some arbitrary numbers here, making blood pressure say zero point 0.8, age 0.5. But what are the actual values? Well, that's the whole point of an artificial neural network. The data surges through to the output and then backward through the artificial neural network where the real weights are determined. Once you have these values, you know the real value of each output. As an example, you may find that the catheterization ranks 0.9 and ST depression is 0.5. Now the artificial neural network can write an actual algorithm or formula that will incorporate these weights into your ANN so that when you present your own patients, your own data, it can predict with a high degree of accuracy whether or not they have heart disease. Don't worry if this doesn't all make complete sense. ANNs are a completely foreign concept, so we will present this in different ways with some repetition to make sure you've got it. Perceptron. Now let's look at this more closely to be sure we're clear. Since this is the most important concept to understand, let's just go at it again in some greater detail. The neuron now is divided into three parts conceptually, with inputs, calculations in the middle, and outputs, and the overall combination of all these lines in the circle is called a perceptron, input functions. This is where the neuron receives the input from the previous layer of neurons. As you can see, each line represents a value and the weight or importance of that value. This is all summed together in the first part of the neuron and then passed to the activation function, which is where a lot of the magic is. If this is the very first layer to the left, you'll be feeding in values such as pulse, age, cholesterol, and blood pressure from the input layer. Again, if you use spreadsheets regularly, you're putting your spreadsheet on its side and adding the header for each column into these X inputs. Activation function. This calculation is performed on the sum of these inputs and determines what value will be passed on to the next neurons, or if no output at all will be passed on. We'll look at several of these. Output function. This is the number of neurons you will output to in the next layer. As you can see in a fully connected neural network, this value would go to every neuron in the next layer. To be clear, a numerical value enters the left side of the neuron. The neuron sums up the weighted inputs from all the other neurons. So the first layer after the input layer would have inputs from every one of the neurons in the input layer. So blood pressure, blood sugar, pulse, sex, age, cholesterol, etc. would all connect to every one of those neurons. After receiving these inputs, they're summed up. Then the activation function determines how much of that value, if any, is passed on to the next layer of neurons. The output function takes this number and passes it on to the next set of neurons. The final output function at the very end of the neural network to the right is the result or the Y value. So in the case of predicting heart disease, there will be just one output, yes or no, heart disease or no heart disease, if you're calculating a binary output. And again, binary is just a simple way of saying you have two choices, yes or no, 0 or 1, heart disease or no heart disease. You could also output categories such as stages of heart failure or classes of heart disease, as we'll see. In a more advanced example, ANNs can classify pictures, identifying dogs from cats, or handwritten digits, or read MRIs, chest x-rays, and mammograms. Perceptron mathematics. Have a look at what a perceptron looks like mathematically. Pretty daunting and awfully confusing and intimidating. The neuron doesn't really exist as a neuron, but as a mathematical function. While the math behind it involves complex linear and matrix algebra and ability to input matrices and differential calculus, the bottom line is simple. Now look at a simplified scheme. For most, this is all you'll ever have to know, since it's highly likely you won't ever have to code an artificial neural network from scratch, thank goodness, and will use an off-the-shelf program or a high-level library like Keras, which we're going to see. We'll describe these in much greater detail and show you two great models. Just keep this outline in mind since you'll learn how to do each of these. Preparation of clean data, medical data being very tough and error laden, set nodes to X values, that is the blood pressure, pulse, cholesterol, what weights to use, how many deep layers to choose, then you're going to choose, as we'll see, an initializer, you'll choose a regularizer, you'll choose which activation function to use, how many epochs or times through the network, what the batch size is, the learning rate, the size of the test and training sets. That's it. After you've run your model, as you'll see, you can then tune your model to gain better performance. Here are a few of the parameters. You can vary the batch size, that is, how many examples you put through at a time. You can vary the number of epochs, how many trips through. You can vary the learning rate, whether it's fast or slow at learning. And you can add or subtract additional deep layers, and of course, neurons within those layers. So that's it. That's all you're actually going to have to do in all likelihood when you become a deep learning scientist at a major corporation. So keep that overview in sight and don't get lost in the incredibly granular level detail. Setting weights. How do you know what the weights are that you should apply to each neural input or each neuron input? You don't know for sure, and that's a great beauty of an artificial neural network. Using back propagation, the artificial neural network will figure all of this out for you. So instead of trying to guess how much more important blood pressure may be than, say, blood sugar, the ANN will tell you which for your specific patient population. So let's come back to the big picture to keep your head above the detail here. As a bottom line, the whole game with a neural network is determining the value of each input. That is, how much is it really worth? Is cholesterol 10% of your heart disease risk, or is it 50%? The ANN figures this out because it figures out what the weight is. That is, it creates individual weights for each input, from age and sex to cholesterol and high blood pressure. This gives you the most important features. Finally, the model will create a formula that incorporates all these individual weights. You can then use this formula to assess new patients and what their risk might be. So you might ask, why design a new artificial neural network for the same data we all know so well, say for heart disease? It's because different groups will have vastly different weights. For example, a young heart attack patient will skew heavily towards family history and certain genetic traits, and perhaps a vexing lipid picture. Lipids, of course, being cholesterol and triglycerides. Where a group in their 80s might skew heavily towards age and the prevalence of known coronary artery disease and events. African Americans will have very different risk profiles from Asians and Europeans, which is why clinical trials and medications have to be designed specifically for the population in mind. The ANN may also find new factors that you might not have considered, such as a genetic marker or a metabolic product, which makes them a very exciting source of new discovery. These are simple and straightforward ANNs that you can create for your own practice or hospital. Bias. While weights are applied to each individual input, like my blood pressure, you can also adjust all the weights going into a specific neuron by adjusting what's called the bias. So while there are individual weights that apply to each input, bias is applied to all these inputs. Why? Bias value shifts the activation function to the left or right to better fit the data. And so again, this is an arbitrary adjustment that you'll have at your hands to be able to make your ANN better. The right bias input allows that neuron to fire more easily. This could also be thought of as the intercept applied to a linear equation, changing the placement of the line, left or right. You'll likely not have to use these, but if you want to learn more, it's all explained in the excellent Keras documentation at this URL. Initializers. As you set up your ANN, we saw the most crucial piece was calculating the weights, since these determine the importance of ranking each feature, like blood pressure or blood sugar. So how do you set the initial weights, since you probably don't really know what their rankings are? So this is very easy to do in a program we're going to see, a library we're going to see, called Keras. While there are many initializers, the most frequent one is called random. As you can imagine, this means that random values in a very small range are going to be assigned as weights to every input to a neuron. These weights are all updated with each epoch or pass through an artificial neural network until the ANN can approximate the high degree of accuracy that you're striving for. Only after many, many passes through the ANN do the weights accurately reflect the importance of each feature. As we said, be sure to choose random weights within a narrow range. Then the ANN uses back propagation to use the power of the ANN to determine values by trying millions of different combinations. So here's what the code looks like. This is called initializing your ANN. Specifically, these are called layer weight initializers. I don't know where they came through for these names, but I'm sure they were put there just to confuse us and keep some people away. Okay, so they didn't have a great marketing person making up the names. The actual functions are much easier than the names that they use. So what would you use as a command? You would write down from TensorFlow, keras.keras, import layers. From TensorFlow.keras, import initializers. Layer equals layers dot dense, parentheses, units equals 64. Kern underscore initializers equals initializers. Random normal, standard deviation of 0.01. Bias initializer slash 0.0. Again, the bias, again, we don't know what that is. We don't know what the weighting is, how you shift that around. So we're just going to start with the 0 and see what the system comes up with. So now what do these commands actually do? It probably looks like Greek to you. It certainly did look like Greek to me when I first looked at it. We're able to set initial weights with a small difference between them. They are set randomly with the command random normal. The standard deviation of 0.01 is set with, again, the command 0.01 or equals 0.01 or stddev equals 0.01. Now we call this cookbook code since you need not know how to program in Python. Just cut and paste the code if you have to. You'll see that you are also initializing bias. There's also a shortcut for all of this, which is keras.initializers.random underscore normal. This normal randomization may be all you ever need. However, there are several other options. You can read the documentation in Keras, which is excellent. It's just www.keras.io. Random uniform, truncated normal, zero class, ones class, chlorite normal, identify, orthogonal, constant. Normalization. Why are you making this common scale? Here's why. Let's say you're going to be looking at the effect of age and income on health outcomes. Age might range from, say, 0 to 100 years of age. Income might range from $20,000 to $120,000. The vast difference in scales would throw off the operation of an artificial neural network. The accuracy might be as low as 40% without the normalization and jumps to greater than 80% with normalization. That is putting everything in a common scale. So all values are adjusted to this common scale through the normalization function. Layers. Again, and it's worth repeating, neurons are organized into layers beginning with an input layer. This input layer means just that, a top to bottom layer of neurons. This is where you input your data with each neuron representing an X input value from your Excel spreadsheet. You see these on the left. On the right-hand side, you see the output layer, which is where your results are produced. Between these two is the magic, the hidden layers, the deep layers, which is why we call it deep learning. These hidden or deep layers are what produce the complexity in neural networks. The more deep layers you have, the greater the accuracy of your system. And it's again where you get the name deep learning from these deep layers, deep within this sandwich of neurons. The activation function. So have a look at this graphic. At the far left, you can see the inputs into the neuron. You can see that each of these is modified by a weight and then fed into a neuron as a number. The neuron then sums up these numbers together and determines if they hit a threshold, allowing them to pass to the next neuron, or if they fail to hit a threshold and therefore are not passed on. Selecting an activation function. First, let's look at threshold. So for simplicity, let's look at this most basic activation function. It's just either on or off. That is, it passes the information on or it doesn't. Have a look at the graph. You can see the line is a 0, then a step function comes up to 1.0. If all the inputs in the neuron reach a threshold above 0, The threshold is hit and the activation function triggered. For a binary threshold, the threshold function is a very good choice because, again, it's on or off, yes or no, 0 or 1. Sigmoid. Let's look at something a little bit more sophisticated. The sigmoid function is a neuron and it delivers a much smoother output than the step function. A small change of the input only causes a small change in the output as opposed to the step function, which is enormous, on or off. There are many functions with the characteristic of an S-shaped curve, which is so characteristic of the sigmoid functions. The most commonly used function is the logistic function. The sigmoid is good at forcing a value, either higher or lower, so that a definite yes or no answer can be output. For small values, the sigmoid will return a value very close to 0. For large values, the sigmoid would force an answer closer to 1, thus separating your data out. Since this activation function is such a big part of the success of artificial neural networks, which one you choose can be quite important. Here's a table that suggests which one for which application. Again, sigmoid is very smooth and its most popular is the final activation function when the artificial neural network has to provide a yes or no answer, cancer or no cancer, heart disease or no heart disease. Rectifier is one of the most popular and can allow models to train faster. This starts at 0 and gradually increases towards 1. This is my favorite because it makes so much logical sense. It's not all or nothing. It's not forcing a solution. It's a graded, reasonable response to inputs and not overemphasizing those at the top or the bottom of the scale as a sigmoid may. You'll have to consider how values change in your data set and whether you want the regular stepwise function, say for age, or if your biological data prefers a sigmoid function, such as pharmacology. Now, this is called a ReLU. A leaky ReLU allows for values below 0. Hyperbolic tangent is very similar to the sigmoid function. Here's the difference. The sigmoid function goes from 0 to 1. The hyperbolic tangent value goes from below 0, that is minus 1 to 1. This is a great adjustment if you have a lot of negative numbers and you find your artificial neural network is getting stuck. Softmax outputs the probability distributions of a list of potential outcomes. This is a core principle in deep learning and helps the neural network come to a conclusion about the elements in a classification problem. So, in trying to distinguish which class of heart disease a patient has, softmax would force a clear, discrete answer based on probabilities. You'll often use a combination of activation functions in an ANN. For instance, you may use a linear rectifier function in the hidden layers, and then to declare a binary value, that is a yes or no, a sigmoid or softmax for the final. As a fallback, if you just don't know, ReLU is a great option for deep layers. How do you select an activation function? In Keras, it is as simple as typing the name, in this case, ReLU, in this formula. So you look at this model.add, you have the dense, you have the input, you have the dimensions, and you see where it says activation equals? You just put in the name. It's that simple. So it's like ReLU. We'll look in greater depth at the code for these models, explaining all of these inputs, because this is what tends to hold people back, is not understanding every one of these inputs, and we're going to show you every single one. Optimizers. Now that your model is set up and your data is entered, the most important question is, how do you determine what the weights actually should be? The genius behind an ANN is using an optimizer, such as a gradient descent technique, to determine these weights quickly. Before we start, let's create a mental picture. Remember taking a marble and dropping it into a bowl? The marble went back and forth and back and forth and back and forth and back and forth, up and down the walls, until it settled at the bottom of the bowl. So as a big picture, this is what you're trying to accomplish with a gradient descent, seeking the bottom of the bowl, but in this case a parabola, where the very least error or cost exists. How does the ANN do this? Well, this is where it starts to get very complex. It does it through derivatives. It does it through a very complex calculus. But the best way to understand this formula is looking at the rate of change of the steepness of the bowl, or the slope. So in an ANN, we call this a gradient. your ANN will continue to iterate, looking at the rate of change until the rate of change is 0. This then is the least cost function, which of course is the computer name in deep learning for error. By simply choosing an optimizer, all of this is done for you. If instead of an ANN, you use the specific supercomputer on a conventional statistical model, training might take as long as 16 months. So here are the main optimizers you can choose from. The neural network outputs a result known as y hat. Then the ANN compares the actual y value derived from your data to the expected value. Remember that in training data, you already know all the input variables, like blood pressure and weight, and know the output variable, which is the likely diagnosis of, say, diabetes or heart disease. This difference between the actual value and the calculated value is the cost function, or what is called, again, y hat. Think of cost function as the error. That is, y is the actual value, and y hat is the value we know from the training data. And knowing what it actually should be and what we have, you can figure out what the difference is. So the difference between these two is the cost or error. This is the biggest and most important facet of the neural network, since optimizers determine what the weights really are, help write the final algorithm, and determine the importance of your risk factors or disease class in the case of heart disease. Gradient descent determines this minimum cost function or error. So why learn this? As you improve your model, you'll have the chance to choose different optimizers and which works best. So this understanding will help you make a better choice, choosing the right optimizer. The more sophisticated methods use momentum to take a, again, more sophisticated view of the rate of change. Stochastic gradient descent, the word stochastic means randomly determined. So the SGD picks one data point randomly from your data set as an iteration somewhere on the parabola, and then goes back and forth and back and forth. Batch size. Your batch size may vary tremendously, say from a low of 32 to over 40,000. What difference does that make? As your model updates the weights in your model to improve accuracy, it does it with much greater frequency at a lower batch size. So as you tune your model, if you aren't getting the accuracy you want, consider a lower batch size. What's the downside of a very small batch size? You might overfit your model. What does that mean? Have a look at the clear line here between these two sets of data, and then this squiggly, curvy line, which shows overfitting. Your model will poorly predict outcomes with overfitting and is one of the key faults to guard against. Dropout. To make artificial neural networks work better and achieve a higher accuracy, data scientists drop neurons from the ANN. This is an arbitrary output, so one of the commands is to randomly drop nodes at each step during training. This starts at about 20% of neurons and may increase to 50% of neurons. Below 20% doesn't have much effect at all. If the dropout rate is too high, the ANN fails to learn as well as it might. The command is incredibly simple. Model.add, over parentheses, dropout, and then 0.2 is an example for a 20% dropout. As you tune your model, you can easily change this value to 30%, 40%, 50%, and look at the effect on accuracy. Backpropagation. This updates each of your parameters by running backward through your artificial neural network and using a technique like ADAM to calculate the least error or cost function for each set of values. Backpropagation adjusts all of the weights at the same time. This is the key function, which updates weights and decreases error or cost function. What's great about Keras is that backpropagation happens automatically, so there is no need to make any changes in computer code. However, all of the settings we just reviewed have a major effect on the success of backpropagation to setting the correct weights. Cookbook code. So what is cookbook code? Just like a real cookbook, you simply follow the recipe printed out for you. To make bigger portions sizes, for example, I love pancakes, but take pancakes as an example, my favorite food. I'd make a much bigger batch by adding another egg and a half cup of milk plus more pancake mix. With cookbook code, you are given a piece of code, debugged, and checked to run properly. Like adding eggs and milk, you may want to adjust a few of the ingredients. And it is this adjustment that will be your primary role in many corporate jobs, so that your model runs faster and produces better and far more accurate results. That's the approach that we'll take here. Fortunately, somebody has already written all of the code out for you, and trust me, that is a very difficult task. Here's why we use cookbook code for this course. As a student learning just one proprietary platform, you won't have the capacity to easily switch to another when you land a job. Employers will want you to have a general familiarity and to know the common vocabulary of deep learning. So if you learn the Microsoft Azure system, which DeVry uses as an example, you may land a job using Google's TensorFlow, which you will then have to learn. The best and most universal approach is to use a common data science language, Python, and the key Python library, Keras. We're going to take this approach, this cookbook approach, which is literally just as good as a codeless platform, or better, because you can dive under the hood and look at key functions to fully understand them. Now, the heart of this course is that you understand neural networks thoroughly. The mechanics will come easily once you have mastered the concepts. In this course, I'll show and explain the code. In the follow-up courses, we will teach you to cut and paste that code into a working platform where you can then modify it to run your own programs, debug it, and get it to run faster, more efficiently, and more accurately. Of course, if you can prefer, you can code along right now in the course to get a sense of the great satisfaction of seeing terrific code run and spit out amazing results. You'll find that the difficulty is in understanding the code syntax, which is why we went over artificial neural networks in such great detail above. Python. I just love Python with its simple, sparse code and fun applications. Across a variety of sites, Python ranks as the #1 language for deep learning. Python ranks second overall, just behind JavaScript, which is used for creating web pages. Let's look at why. Python has a tremendous number of features and a robust quality of code, which is easy to debug in development environments like Anaconda or within the Microsoft Azure platform. I find Python incredibly productive since I spend so much less time coding and debugging. Even though it's very technologically advanced, it's a very easy and logical and even fun language compared to, say, Java, which can be incredibly difficult for a beginner. Python's greatest strength is the extensive libraries for machine learning. Think of these libraries as apps, like you buy for the Apple App Store or iPhone stores. The only difference is that they don't have the wonderful graphical interface. Instead of pushing buttons on wonderful looking icons, you'll have to actually enter the values yourself. But they're just as slick, much faster, and far, far more powerful. The key Python deep learning library is Keras. We'll use the libraries for machine learning as well, specifically NumPy, which sets up vector inputs, Pandas, which sets up data frames. These are the structures for data, so it's properly formatted for inputs. Seaborn and Matplotlib allow you to visually explore your data before you set up a model. You can refer back to the machine learning course for more detail. There are many approaches to building an artificial neural network. You can literally write one from scratch in Python, which allows you to fully understand nearly every last facet of the calculations. There are also plug-and-play platforms we mentioned, where you simply feed in your data and only have to fine-tune the system to get the most accurate possible results. Finally, there's Keras, which is becoming a gold standard. This is a Python library and an incredibly easy and fun way to create artificial neural networks. Just a few lines of code, literally as few as 10 lines. However, just as we saw in machine learning, the key is then entering variables to change the shape and outcomes of the artificial neural network. We call this a high-level approach, since it is close to the way that humans communicate. A low-level approach is closer to the dense code computers use to operate. Keras. This extremely popular Python library runs on top of TensorFlow, which is Google's deep learning platform. Tensors and matrices are the mathematical shape perceptrons feed into the deep neural network. TensorFlow takes care of the low-level and incredibly difficult and technical programming necessary to run your code in your CPU or GPU. As we've seen in the computation of the gradient, the key and most important calculation, since this calculates the smallest errors in the model and allows it to assign weights. Another key advantage with Keras is its speed of modeling. I can write a complete neural network in just a few lines and from memory, or follow the recipe in the cookbook. This allows you to try many different ideas quickly. What we will focus on are the things that you can change rapidly and easily to improve your results. This wonderful Python library allows you to quickly set up artificial neural networks. Keras is the most used deep learning framework and the one we'll use because it gives you universal access to most important platforms. You can use it on top of the popular platforms TensorFlow, Microsoft Cognitive Toolkit, R, Theano, or PlatML. Keras is both fast and very user-friendly. As a high-level application, it doesn't require any programming experience. Keras doesn't have a graphical user interface, but still just as simple in terms of adding functions and inputs. Examples of key functions are optimizers, activation functions, data frame dimensions, input and output dimensions, numbers of dense layers, length of dense layers, size of training and test sets, and finally accuracy. If the information starts from the left as the input of an X variable and proceeds all the way to the right end, predicting a Y outcome, this is termed a feed-forward neural network. The signals can only travel in one direction, forward. Input data passes from the input layer into deep layers where calculations are performed. Each neuron makes computations based upon the weighted sum of its inputs. The new values become the input values that feed the next layer in the feed-forward system. This continues through all the deep layers and determines the output. Feed-forward networks are often used in, for example, data mining. The artificial neural network. This is the simplest and easiest neural network to learn. It's best for analyzing the kind of data you encounter in healthcare, such as predictive surveys for heart disease risk. These are the main applications for exploring static data. Here's an example. This Cleveland Clinic data set is frequently used as a training example for heart disease. The output is binary. The patient either has heart disease or not. Let's take a look through this to better understand it. We'll begin with a data set which is easily downloaded from GitHub. Heart disease binary. So these three columns show the key input features for the artificial neural network. The first is the actual feature, the second, a description of it, and the third, the type of data. So let's look at a few of these. Age. This is a key risk factor since the older a patient is, the more likely they are to suffer from heart disease. The feature type is a simple number, say age 72. CP rates the kind of chest pain, the key symptom of a heart attack, or what doctors call angina, the chest pain associated with heart disease. You're familiar with standard risk factor measurements such as resting blood pressure, fasting blood sugar as an indicator of diabetes, resting EKG, which may display an old heart attack or insufficient blood flow through a part of the heart. This then gets more sophisticated, looking at the maximum heart rate reached during exercise stress tests, whether chest pain can be evoked with a stress test, and changes in the EKG. The last ones are even more sophisticated scans. Now, let's look at feature types. Numerical or simple numbers like age 72, blood pressure 130/76, cholesterol 182. Categorical results classify data. As an example, exercise is either inducing chest pain or it isn't. The final value is the target or output. The value of this data is that we know what the actual outcomes are from the Cleveland Clinic data set. The patient had heart disease or they didn't. This is a binary output. Once you have run your artificial neural network, you can look at the errors it has and correct them toward the known target output to vastly improve your accuracy. Thank you so much for watching this course on deep learning and medicine. In our final introductory course, we'll first look at creating a categorical model for predicting the class of heart disease a patient falls in, and then we'll look at the most fabulous and useful part of all of deep learning and medicine, computer vision, with the ability of a computer to read MRIs, CT scans, mammograms, eye scans, and X-rays with a far greater degree of accuracy and speed than any radiologist. See you in our next course.